Well, I guess it's nicer up here in particular, in the part I'm not showing quite yet. But if you take a look, you know, it's like, why do that earlier? Do it when you have to, right? So that's maybe a little nicer, is just deal with the cosine squared, but it's the same kind of stuff. She wrote negative the fraction, and I just reversed it. But then, yeah, it all disappeared, huh? When you plug, well, we knew it would. We knew it would when you plugged in. So that's kind of cool. Do you guys
we don't have to take the next test then, right?
What test?
Yeah.
We're working on a project. Okay. So we just finished section 15.4 on triple integrals, right? In theory? Okay. So now it's time for 15.5, which is triple integrals, again, with other coordinate systems. I think this is a cool section. So you're going to see two types of coordinates. The first one is called cylindrical. It is. Polar with a z, that's right. They're going to say r, comma, theta, comma, z. And what the claim is that any point anywhere in space, here, let me throw this point at you. You can, if you know the z coordinate, right, you can just, you know, figure out what theta is and figure out what r is, and then you have z. And so we're going to then do integrals where we integrate, right? Okay. And so suppose I have some d where I'm going to integrate dv, some function of x, y, and z. Well, maybe that doesn't work so well, but what you can do sometimes to make that life easier is change the x, y to what? R and theta. Keep the z what it is. And now you're in the world of what's called cylindrical coordinates. If I do that, when I go ahead and make the change from dv into the world of, let's see, what would the iterated integral look like? Well, yeah, you might just throw a dz there, right? But you're right that not only do you need a dr and a d theta, you need another r. The pirate is back. Okay, I mean, and again, I hate that explanation. We'll get to what the explanation really should be, but that's not till the end of your chapter. So it'll be fun. You guys will love it. You'll say, "Wow, thanks, Paul. thanks for teaching us that, and that was great." Now, the other coordinate system. This is where I said, okay, maybe there is 20% that I can teach you. It's called spherical coordinates.
That's the real polar coordinates.
No, these are...
Really?
Well, they're different.
So are we using...
Well, okay.
I think it matches up better.
I can see what you're saying. I mean, you know, I guess I could see what you're saying, because in the world of, you know, 3 space, you know, because here's the point that Sullivan's making. He's saying, look, why do we use r and theta? Because we're all about circles, right? In R2. Maybe circles are sometimes nicer than rectangles. So maybe in R3, what you're saying the analogy is maybe a sphere with that green equator. Can you guys visualize that, or is that just a horrible drawing? It's pretty bad. Yeah. That's awful. Let me try again. Here we go. There, green equator. Looking better, Paul. And then let's throw the axes in there. Okay, so let's see. You know, when you do the doot-doot, it helps. So try that if you guys are stuck at home. All right, so there we are, right? So how do we represent a point in spherical coordinates? Well, go ahead, question?
Yeah, I'm looking at these these coordinates, and I'm seeing theta, and I'm seeing two other Greek letters. Is one of them like lowercase?
I was just going to get to that. So row, as in row your boat? No, as in here's the deal. If we want to represent some point in space, so kind of like the very first thing we do in cylindrical coordinates is r, they didn't want to use r down here because they thought you'd get confused. So they went Greek, right? A lot of people in college like to go Greek. So that's what they did. They said, what's the Greek letter R? It's a rho. Does my rho look like their rho? Let's see. Looks like a P. Well, it's an R. Thank you very much. It's actually rho. Let's see what theirs looks like. Where did 15.5 go? Did I not download it? No. So, let's show you in the book.
It does look like a P, lowercase p.
Theirs does?
Yeah,
Or mine does?
both.
What? Well, whose looks like the Greek R then?
Both.
Both. That's the right answer, Matthew. Here we go. Check that out. That's rho. Hey, here's the equation. Rho equals A. If A is greater than 0, you get this. What's that supposed to represent? Yeah, kind of like if I give you the equation R equals A, you would have a circle of radius A. Right? So the first coordinate is going to be rho. Okay? Then the second coordinate is not theta. The last coordinate is theta. And that's the good old theta that we've always had, by the way. Which is what? Well, it's kind of measuring distance, or it's measuring angle like it did here. Around, if you rotate around the green equator, let's say. Okay? But I claim that that's the last thing we want to think about. Matter of fact, when you visualize spherical coordinates, it might help you to think about the equation theta is pi over 2. What is theta is pi over 2? Straight up on the y-axis. Now, where's the y-axis on my picture? To the right, right? So that's y. So when I say theta is pi over 2, I'm telling you that, well, I'm somewhere actually in a plane, right? When theta is pi over, because rho could be negative, just like in polar coordinates, r could be negative. If rho is negative, then you shoot the behind-the-back pass. You guys have seen that in polar coordinates? No? I may have to show that one of those. I may have to do problem 43 from the homework. That's actually a good example of it. So anyways, I'm claiming that this plane, which plane? The YZ plane, is where you are when theta is pi over 2, right? So if rho is the distance to that sphere, right? This could be rho. Or this could be rho, right? Those are both rhos. Well, so you could say rho equals A is the equation of the sphere. Theta tells you where you are when you... You know what theta is telling you? It's telling you which longitude you're at. Are you with me? All right, so what's the only other thing I need? Latitude. And we need another angle. And of course, in the world of cartography, what we did was we measured latitude as a positive or negative number from the equator. But we don't do that anymore for spherical coordinates. Now what we do is we want this angle here, which we're going to call, well, it depends. You could be, phi or phi. It's this one here. You guys know that Greek letter?
Yeah, we've seen that before. It didn't look like that the last time.
You think I drew it this way last time?
It looked more like a circle with a line through it. Completely. Yeah, like completely through it.
How's theirs look? I'm trying to draw that. How am I doing?
Yeah, the phi that I've seen before was in the trig book.
Okay.
And it looks different. but same
Phi usually a constant.
Well, for us, phi or phi doesn't really matter which one you call it, because in Greek it's only the first letter that is telling you the symbol. Rho is an R. Phi is a PH sound, right? So, sounds like an F, I guess, right? So that's the symbol. What that is measuring in spherical coordinates, we want phi equals 0 would be pointed literally straight up the z-axis. And we're measuring down from the North Pole. Okay? So what's the range for phi? I guess phi has to be between 0 and, let's just only go up to pi over 2 for phi. Because that's, once you get below there, if you go any farther, you could have measured it with a smaller angle and choosing a different value of theta. Theta is going to be between what and what? Still 0 and 2 pi, like it always has. And rho, I guess you could require rho to always be positive, right? As long as you aim the right direction. But if you allow rho to be negative, then you're going to have multiple representations, just like you have multiple representations in polar coordinates. So I think those are the main points in terms of theory that we have to get across for next time. And so
Can you say that one more time, that phi measures the angle from?
the North Pole
North axis.
down. Yeah, as a matter of fact, phi is sometimes called co-latitude. Latitude, dude. Latitude. Co-latitude? Let's see if you understand why it's called that. The sine of an angle, what's its relationship to the cosine? Yeah, the reason you say co is because it's 90. It's the sine of 30 degrees is the same as the cosine of the complement, the cosine of 60 degrees, right? So you might call this the co-latitude because, if phi is, say, what does it look like here? It might be like 40 degrees. No, that looks more like 50 degrees. If phi is 50, maybe it looks like that. Well, that's the same as the latitude being 40 in the northern hemisphere. Once you get to the southern hemisphere, then you're between 90 and 180 degrees, right, for phi. So I've heard it called that also. Okay. So yeah, I think the good thing about doing that today is then it just frees me up to just do problems for next time. I think I'm going to finish the class. I have 5 minutes. I'm going to give problem 43 a crack here. And this is from section 14.3. 15.3. Sorry about that. So let's take a peek at it. We're working hard on polar coordinates. We may as well. So here we go. Problem 43 is here. Let me make it big for you. Am I recording anything? Yeah, good. So, sketch each region and use integration to find its area. I have this brand new calculator, which I want to show off. The region inside the cardioid 1 plus sine theta, and outside, what did it say? 1 plus cosine theta. So these are cardioids. You guys study the cardioids a little bit in Calc 2 maybe? Trig. Yeah,
I guess we did.
I like doing cardioids when you first teach polar coordinates because they're great functions to graph just to demonstrate what polar coordinates are. All right, so here's my brand new calculator here. Looks like I was doing stats most recently with it. Let me go to my y equals screen, which is in color. Isn't that cool? Let me change my mode because we want to be in polar coordinates for this problem. So let's see if I go down here to polar. Yeah, I like the color. All right, now when I go to y equals, what happens? If I'm in polar mode, it says r equals. Right. So let's sketch these things. What do we have? We had 1 minus cosine. No,
1 plus sine
1 plus sine and 1
plus cosine.
plus cosine. So let's take a look at them both. 1 plus sine of theta will be in blue, and then 1 plus cosine of theta will be in red. And let's graph them. These are kind of nice. There's a cardioid. Do you see why it's called a cardioid? Sure you do. Let's zoom in. I think zoom in works pretty well here for this problem. You see that? Well, I remember that the zoom works, it's 2.5 by 2.5 in each direction when you zoom in once. So yeah, we have a nice little, and the other thing that's kind of cool here is that you can actually see the table at the same time that you're looking at the picture. So that's one of the nice things about this software, I think. You know, it's funny, when theta is 0, it says that R1 is 1 and R2 is 2, right? You know, one thing that's useful to do here is change the table set. It says, what's delta table? And it says 1. Why don't I do this? Why don't I make it something like pi divided by 8, let's say? And let me look at the table just for kicks. Okay. See, when you do the cosine of 0, you get 0, so 1 plus 0 is 0. But the sine of 0, I'm sorry, the other way around. Sine of 0 is 0, but the cosine of 0 is 1, and that's why this thing's at 2. Do you guys recognize this number, 1.57? Okay, and you definitely recognize this number, 3.14. By the time I'm pointed to the left, my red cardioid is now at 0, right? It has no radius, and that's why in the first pi over 2 it kind of goes from here to here. Right? Okay, anyways, back to our problem. We're supposed to find the area contained where? Inside both. Inside both cardioids? So I guess we're talking about this kind of region right in here, right? One thing I don't know is what about this little bit down here? You know, let's take a look. Let's zoom in a little more.
That little bit is
Let me enter. Here's the first one. Isn't there a little tiny bit of area down in here? I mean, is that being considered? I think so, right? So here's what I want to do, guys. I want to think about some points of intersection. Because, see, as I'm trying to integrate this stuff, what I want to think about is, again, top minus bottom kind of stuff, you know? Like, between 0, which is pointed straight to the right, and whatever this point is up here that they cross, which is what, by the way? Do you know where they cross? It'd have to be where sine and cosine are the same. So sure, pi over 4, right?
and down there, pi over 4.
Then I really want to be inside the blue region, right? But then from here on out, I want to be at the red, maybe until we get to here at 5 pi over 4. And then from 5 pi over 4 to 2 pi, let's say, I think then I'm okay, right? So I think that's how I would do it, is I would think about splitting up the integrals based on moving from points of intersection. So I'd be integrating the blue function, like you said, from 0 to pi over 4, or maybe even back to negative pi over 4, something like that.
But what are you actually integrating? Are you integrating the difference between the two functions because we're finding the space?
I think here we're just integrating particular functions, right? If we want to be inside the blue, what I'm saying is we'll also be inside the red. Here.
But you'll only be inside the red.
Let me do one thing here, which you can do. Second, calculate. Oh, they don't let me integrate. Only derivatives. Okay. I'll need more time. We can return to it if you want. What did he do?
You got it.
He was upset he couldn't integrate. Okay. Well, I'll live with it.
We were happy because that was the one test we got calculators for.
Oh, I see. Yes. So, all right, guys, we are out of time.